In an earlier lesson, we looked at arithmetic sequences, which was when the sequence had a constant addition or subtraction between the terms. In this lesson, we look at these things called geometric sequences, and that's when you have a constant multiplication or division between the terms, and we call that the ratio. So in a geometric sequence, the ratio between each pair of consecutive terms is the same. This ratio is called the common ratio. Just like when we had arithmetic sequences, we called it the common difference. The way that you find each term is you multiply by the ratio. So if you have 5 as your common ratio, each term is found by multiplying by 5. There's a pattern, but the pattern is very specific. It's a multiplication pattern. So in example 1, my question to you is, what are you multiplying by to go from one term to the next? Now, you might say divide by 2, but that wasn't the question that I asked. What I asked you was, what are you multiplying by? So that means that you have to think about what it would be as a fraction, and the fraction that you're multiplying by is 1/2. So that means that you're multiplying by 1/2 each time, which means that it's a geometric sequence, and so that answers this question because it says determine whether it's a arithmetic, geometric, or neither. And then we say why, because it says to explain. We say that the ratio is 1/2. Now in letter B, it's definitely not being multiplied by the same number, but is it arithmetic? So it looks like it's not, because it would be +4, then +5, then +6. So it does have a pattern, but it's not arithmetic or geometric. Because we can probably use the pattern to find the next term, but that's not what they're asking about in this example. So I said it's neither, and the way that I described it was that it doesn't have a common difference or a common ratio. So it's not arithmetic and it's not geometric. So now in example 2, they give us geometric sequences, and they want you to just find the next 3 terms. So what we're doing is you're just going to find that ratio and just extend the pattern. I think you could do this on your own. Why don't you pause the video? The third one was a little tricky. They were multiplying by -1/4. So the next ones would be +1/4, -1/16, and +1/64. I think the first one was pretty simple. Now we did also something like example 3 back when we did arithmetic sequences. We said that the term number was the x value and the value was the y value. So let's see what happens when we go to graph this. So term number is x, and then let's say the number or the value will be y. So term number 1 is 32. Term number 2 is 16. 3 is 8. 4 is 4. And 5 is 2. All right, let's make our graph. We only need to be in the positive quadrant. And I think we can go by 4s. And let's just do this by 1s. Okay, pause the video and plot those points. So I plotted my points. Hopefully now you understand why this lesson is put in the exponential chapter, because it's exponential. And see, this is a picture of me being super surprised that the points become exponential. We're not going to connect the dots because sequences are discrete. Remember, we talked about that a couple of lessons ago. So now that I've told you that they're exponential functions, I'm going to show you this seemingly crazy looking formula that turns sequences into exponential functions. But remember, you all freaked out about the arithmetic sequence formula, and that wasn't such a big deal. So don't worry when you look at the next page. All right, so we have our first term, which is a sub 1, and let's say that's just 1, right? So we have this sequence where you start at 1, and the ratio is 5. So then that's just the made-up example. So the way that you find a2 is you take the first term and you multiply by 5. Then the way that you find the third term is you multiply by another 5. And then the way that you find the fourth term is you multiply by another 5. So what this is saying is you just take the first term and you multiply by the ratio however many times you need to, depending on what position you are in the sequence. And so we end up with this expression right here. So let's rewrite it. It's a sub n equals a sub 1 times r to the n minus 1. And the reason that it has to be n minus 1 is because the first term has an r value of 0. So in order to make that r value cancel out, we have to subtract 1. So a sub 1 stands for the first term. R is our common ratio. N is the position number that you are in the sequence. You could be first, second, third position, whatever. And then a sub n is like the value of the term at that spot. So here's how we use it. Example 4. Write an equation for the nth term for the geometric sequence 2, 12, 72, 432. So we need to find a1 and we need to find r. Well, a1 is always really simple. It's just the first number in your sequence. So a sub 1 is 2. The ratio we have to do a little math for. So you can see it's times 6. So the ratio is 6. So our equation, write an equation, is a sub n equals 2 times 6 to the n minus 1. And that's it. That's the equation. If you wanted to find a specific number in the sequence, you would plug in whatever value of n you wanted. Now down here, it's saying all you can do is instead of saying a sub n, you can write it using function notation and use f of n, but they're the same thing. All right, let's look at one more example. So this is probably something that we've all done on a computer, on a map. You either zoom in or you zoom out, and when you zoom in or out, it actually scales it at a particular ratio. So this says clicking the zoom out button on a mapping website doubles the side length of the square map. So that's an R value of 2. After how many clicks on the zoom out button is the side length of the map 640? So we go over to the side. They tell us if you click once, the map side length is 5. If you click twice, the map side length is 10. If you click 3 times, the map side length is 20. So the first thing that I'm going to do is I'm going to write a formula, because then I can use my formula to figure out how many clicks it'll take until I get to 640 miles. So I need a sub 1 and I need r. Well, a sub 1 is really simple. It's 5 because it tells you that's the first term, right? Second term, third term. So the first term is 5. And then the ratio you could either get from the chart, it's multiplied by 2, or you can recognize in the story they told us that it doubles. So my formula is a sub n equals 5 times 2 to the n minus 1. So that's my formula, but that's not the answer because they want to know how many clicks it's going to take me. So what I will do is I'm going to plug in 640 in for a sub n, because that's like the final answer. I want to know what position in the sequence 640 will be. So the way that you do this is you first freak out, and then after you stop freaking out, you just do your order of operations in reverse order. So I'm going to divide by 5. So I get 2 to the n minus 1 equals, that is 128. And then I need to figure out what power of 2 is 128? So you just use guess and check. Now I have my phone nearby, so Siri's going to help me out. You just, kind of guess and check powers of 2. What is 2 to the 5th power?
2 raised to the 5th power is 32.
Okay, that's too small. What is 2 raised to the 6th power?
2 raised to the 6th power is 64.
Okay, I think one more time. What is 2 raised to the 7th power?
2 raised to the 7th power is 128.
Perfect, I got it. So that's 2 to the 7th equals 2 to the n minus 1. You all found my secret now. So now that the bases are the same, I can ignore the bases. 7 equals n minus 1. So it will take me 8 clicks to make the map length 640 miles. If you have any questions, write them down and ask me when you come to class.